Hello everyone, and welcome to this advanced lecture series on multiphase flow modeling. This particular lecture is based on the wet steam model. Wet steam model is a special category model within the multiphase models available in Fluent. It is specifically meant for modeling wet steams. So let us go ahead with this lecture and discuss the wet steam model, and we will see how to apply the wet steam model within the multiphase flow modeling module of Fluent. Before we begin, let us have an overview of what we are going to study in this particular lecture. First, we will see what is wet steam. Then we will see applicability of the wet steam model. Where do we apply the wet steam model? For what specific problems do we use the wet steam model? After that, we will see the basics of wet steam model. What is the concept behind the wet steam model? How does it model wet steam, etc. After that, we will see limitations of wet steam model. Remember, the wet steam model is specifically meant for modeling wet steam. It is an exclusive model for that. It has some limitations and we will discuss those. In the end, we will also see what are the user inputs for the wet steam model and how to set up the wet steam model within Fluent. We will end this lecture with references that we have used for preparing this lecture. So what is wet steam? When we say wet steam model, what exactly is wet steam? Wet steam is basically a mixture of liquid and steam. We have to remember that both these liquid and steam are at saturation temperature. If we go on heating a substance in liquid state, a mixture of liquid and steam will be formed, but both will be at saturation temperature. That is, the liquid will go on heating up to the saturation temperature, then steam will begin forming, but at saturation temperature only. So, at saturation temperature, as we go on adding heat, liquid and steam, a mixture exists at that temperature before the entire steam is formed, and that particular mixture is known as wet steam. Now, if we add more heat to the wet steam at constant pressure, the temperature remains constant until all the liquid is evaporated. This is referred to as saturated steam. Again, after this, if more heat is added to the saturated steam, temperature increases above the saturation temperature. This is called a superheated steam. So what we have to remember is initially we have a wet steam at saturation temperature, which is a mixture of liquid and steam. If we add more heat to this wet steam at constant pressure, the temperature remains constant, but the liquid goes on converting into steam. That is, the liquid goes on evaporating. When all liquid is evaporated at the saturation temperature, we have saturated steam. If we add more heat to the saturated steam, temperature increases above the saturation temperature, and then we have the superheated steam. Let us see this process on a temperature versus enthalpy diagram, which is usually found in steam tables. First, we have subsaturated steam. As we go on increasing temperature, the enthalpy increases. We have saturated water and dry saturated steam, and here we have the superheated steam. So in between the subsaturated water and superheated steam, we have the wet steam. Now let us see, where do we apply this wet steam model? What are its uses? Which type of problem do we solve using the wet steam model? When steam expands, it also gets condensed shortly after it crosses the vapor saturation line. Due to this expansion process, even the superheated dry steam first subcools and then nucleates to form a two-phase mixture of saturated vapor and fine liquid droplets. This is thermodynamically defined as wet steam. Now, modeling of wet steam is very important in the analysis and design of steam turbines. If there is wet steam at the steam turbines exit, it can cause severe erosions to the turbine blades. It can also lead to reduction in aerodynamic efficiency of the turbines, which overall degrades the performance of the steam turbine. So modeling of wet steam is extremely important to see whether we are getting wet steam presence at the exit of the turbines or anywhere in the steam turbines. This wet steam model is specifically used to model such conditions or such situations. Here let us see basics of the wet steam model. We will see the basic concepts and which type of equations are solved. First of all, we have to remember that wet steam model is an Eulerian model. That is, it uses the Eulerian approach. Eulerian equations are solved for all the phases involved. In addition to the Eulerian equations, two additional transport equations are solved. One transport equation is solved for mass fraction of the condensed liquid phase, and the other transport equation is solved for number density of the droplets per unit volume. These are the two additional equations solved. in addition to the Eulerian equations. Now there is also phase change involved within the wet stream model. There is formation of liquid droplets in homogeneous non-equilibrium condensation process. In order to model this, a classical non-isothermal nucleation theory is used. If you want to study details of this classical non-isothermal nucleation theory, please refer any of the advanced multi-phase reference books, or you can also refer the theory guide of Fluent Software. In this particular lecture, we will only restrict our discussion to the applicability and the usage of the wet stream model. We will not go into detail of all the internal equations involved or the internal theory involved. After studying the basic fundamentals, let us discuss limitations that are associated with the wet stream model. First is, the wet stream model can only be used along with the density-based solver. So you have to activate the density-based solver first in order to activate the wet stream model. Also, less number of boundary conditions can be used. Only the pressure inlet, mass flow inlet, and pressure outlet boundary conditions can be used. The rest of the boundary conditions cannot be used with the wet stream model. And the next restriction or limitation is with respect to the materials or material dialog box. Now, when we use the wet stream model, we have to use a built-in steam property function or a user-defined wet stream property function. So, whenever we activate the wet stream model, the material panel or the material dialog box will become restricted. That is, we cannot go in and change any of the materials because we are already using a built-in steam property function or a user-defined property functions. So we cannot change or modify the materials later on. So if solids are involved in our problem, we have to define the solid properties before we activate the wet stream model. After that, we cannot change the material or the solid properties. So remember to define the solid properties before activating the wet stream model. In this slide, we will see how to activate the wet stream model. In order to activate the wet stream model, first we have to activate the density-based solver. For this, we go into problem setup, then into general, and then we click on density-based solver within the solver section. After this, we go to models, multi-phase, and then click on edit. That is, within the problem setup, we go in model, we click on multi-phase, this panel will open up, and here we select the wet stream model among the list of multi-phase flow models. After activating the wet stream model, let us see what are the user inputs that we need to give in order to set up the wet stream model. The first of such user inputs is the UDWSPF. Now you will wonder, what is this? UDWSPF stands for User Defined Wet Stream Property Function. These functions are state property functions that we need to input in order to define the thermodynamic behavior of the wet stream. Fluent allows you to use our own property functions and data with the wet stream model. We can do this by uploading or compiling the user-defined wet stream property function or the UDWSPF. We define the wet stream equations of state. So basically, these user-defined property functions are to define the wet stream equation of states and all the related thermodynamic data and transport property equations. So all these data is contained within the UDWSPF. For this, we have to create a C source code that conforms to predefined format. Then we start a Fluent session and set up the case file as usual. After this, we turn on the wet stream model. Then we compile our created C source code, that is the UDWSPF C function, and build a shared library file using a UI command. That is, we say define, then model, multi-phase, wet stream, and then we type in compile user-defined wet stream functions. This builds a shared library file. Then we load the newly created UDWSPF library using the UI command define, models, multi-phase, wet stream, and then we type load unload user-defined wet stream library. Then we run our calculations. So this is the entire process of creating a UDWSPF and uploading it in order to define our own user-defined wet stream properties. In this slide, we will see how to compile the UDWSPF C code. First, we have to write the C code for our user-defined wet stream property functions. After this, we place that C code in the working directory. Then we launch ANSYS Fluent as usual. We read the case file that we want to solve. After that, we can compile the user-defined WetStream property function C code and build a shared library using below commands. We will see these commands one by one. First, we define models, that is the WetStream model, by going into Define, Models, Multiphase and WetStream. This is the standard procedure to activate the WetStream. Remember, before this, we have to activate the density-based solver. After this, we select the compiler user-defined WetStream functions option. Then, we enter the compiled user-defined WetStream property function library name. Then we continue on this procedure when we are prompted from Fluent. Then we enter the C source file name. We enter the header file name if applicable. If we do not have an extra header file, then we press enter when prompted. Once all this is done, Fluent will start compiling the user-defined WetStream property function C code and it will put it in the appropriate architecture directory. So this is how we compile the user-defined WetStream property function. Next step is to load this user-defined WetStream property function after compiling it. For this, we perform the steps that are highlighted in this slide. We go to Define, Models, Multiphase and WetStream, that is we activate the WetStream model. Then we select Load Unload User-Defined WetStream Library option and follow the procedure that is prompted after we select this particular option. If we are able to load the user-defined WetStream property function after selecting this option, this is the message that will come in the text window. Once this message is displayed, it is confirmed that we are able to load our user-defined WetStream property function lab. When we use the WetStream model, there are some additional user inputs that pop up into the boundary conditions panel. These additional inputs are also required at solution initialization or patch dialog boxes. We will discuss these additional inputs in this particular slide. First is the liquid mass fraction, which is the mass fraction of the liquid entering or exiting at that boundary. This is also referred to as wetness fraction. Usually when we define inlet boundary conditions, this is entered as 0 as we assume that there is dry steam that is entering at the boundaries and wetness is 0. Next additional input is log 10 or droplet per unit volume. These are the quantity of droplet per unit volume. This is also usually entered as 0 as we assume that 0 droplets entered the domain at the inlet. You can see pressure boundary condition panel here and these are the additional inputs that are appearing. That is liquid mass fraction, this particular value, and log 10, that's droplet per unit volume, which has a unit of per meter cube, is appearing here. So with this, we are at the end of this particular short lecture on WetStream model. We will summarize what we learned in this particular lecture. We studied the WetStream model and its applicability, that is what exactly is the WetStream model and where do we apply or use it. We also discussed additional user inputs that are required for WetStream model. We discussed how to input the user-defined WetStream property function C file. We also discussed some boundary conditions that are required which are specific to the WetStream model. Please note that this lecture was an introduction to WetStream model. The WetStream model is a highly exclusive and specific model and it is meant for specific applications only. So we had a very narrow perspective while studying this particular model. Whenever you need to use it in actual problem, it is always recommended that you go through the user's guide as well as the study guide to know more information and to go into detail of this WetStream model. Currently, we restricted our discussion only to the introduction of the WetStream model. So with this, we end this particular lecture. These are some of the references that we used while preparing this particular lecture. So thank you for viewing this particular lecture. See you in the next lecture.